So today's session is going to be about lattice energy, electron affinity, and born-haber cycle. Okay, so when we look at lattice energy, okay, we need to understand what is lattice energy. Okay, so you can see the definition, okay, of the lattice energy is written over there. It's going to be the enthalpy change when 1 mole of ionic compound is formed from its gaseous ion under standard conditions. So you can see over here that when we have a gaseous ion, so for example, okay, sodium ions and then Cl minus ion, you are going to actually form 1 mole of sodium chloride. Okay, so you can see the second example, okay, as well. Okay, but if let's say I want to write down the lattice energy, okay, the equation. Okay, for example, I want to write the equation for aluminium oxide. Okay, aluminium oxide, how do I write? Okay, so aluminium oxide, to form 1 mole of aluminium oxide, okay, I am going to use, okay, the Al3 plus, okay, and then O2 minus, okay. How many moles? Okay, I have 2 moles, so I just put 2 there. How many moles over here? I put 3 over there. And this one must be in gaseous form, okay, gaseous ion. So I just put gas and I put gas. Okay, this is going to be the definition, how to write the equation, okay, for lattice energy. But what is important over here, you need to always remember that lattice energy is going to be always going to be exothermic. Okay, always going to be exothermic. Okay, I'll write down exothermic. Okay, why this is going to be always exothermic? Okay, I'll explain. Okay, because okay, it's related to what we call as forming bonds. Okay, you can see sodium ions, okay, and Cl minus ion, they are joining together. Okay, they are forming bonds. Okay, so I think for my students, I teach them when 2 ions or 2 atoms come closer, okay, they like to move. Okay, they have kinetic energy, high kinetic energy. And then when they join together, okay, they are stuck. Okay, so all this energy must be released out, okay, in form of heat and so on. So heat is released. Okay, so this is going to be, you can memorize. Okay, this is bond making. You can memorize. Is going to be exothermic, and bond breaking is going to be endothermic. So always remember lattice energy, because it involves bond making, is going to be exothermic. Now, I will actually move on, okay, to the factors affecting lattice energy. I'm very sure that you have learned all this by now. Okay, it's just a review. So you can still see the definition is over there. Okay, but when we look at factors affecting lattice energy, now I told you lattice energy is always going to be exothermic. Okay, but it will be more exothermic when what? Okay, it will be more exothermic when we are dealing with smaller ionic size. Okay, and when we are dealing with greater ionic charge. Okay, so if you look into this, okay, we are generally referring to what we call as charge density. Now, what is charge density? If you look at any kind of density, it's going to be mass over volume. Okay, but if you are looking at charge density in chemistry, it's going to be something like charge divided by volume. And this volume, okay, you can use radius, okay, as a direct representation of the volume. So if you have a smaller ionic charge, if the volume is less, okay, the volume will be less. So the charge is going to be spread out in a smaller volume. So when the charge is spread out in a smaller volume, okay, you can say that the charge is very much positive. For example, positive ion is very much positive. And then the negative ion is very much negative. So if I want to form bond between them, okay, the bond will be much more stronger. There will be a stronger attraction, electrostatic forces of attraction that will exist between them. So because of that, okay, more bond forming. So if you have more bond forming, I told you bond forming is going to be exothermic. That's the reason why it's going to be more exothermic. And if you are looking into greater ionic charge, similar concept, okay, if you are having the same, if you are having the same charge, okay, sorry, if you are having the same size, okay, this one is the same, okay, but if you are having more charge, okay, the charge is going to be more. So what does it mean? In that particular volume, you are having more charge, okay, so it will make this to be more positive, the same as here. You will have more bond forming, and then the electrostatic forces of attraction will be greater. So that's why, okay, when we are dealing with a smaller ionic size and greater ionic charge, we are going to get a more exothermic lattice energy. So I will move on. Okay. So if you look at the checkpoint over here, okay, if we can just do it together. Okay, you see here, write the lattice energy equation for sodium oxide. Quite simple. Okay, refer to the definition. Okay, sodium oxide. So you are forming sodium oxide, Na2O. Okay, solid, and you are forming from the ion, and the ion must be in gaseous form. Okay, so gas. Okay, gas. And this is going to be 2 minus, you have 2, so I put 2 there. Okay, as simple as that. Okay, magnesium bromide, okay, MgBr, MgBr2, okay, solid. So you are going to get it from Mg2 plus and then 2Br minus, and make sure to put gas and gas. Magnesium sulfide, okay, Mgs, okay, solid. And you are going to get it from Mg2 plus and then S2 minus. They must be in gaseous form. Okay, so you write down like that. Okay, so now if you want to compare the lattice energy of magnesium oxide and lithium fluoride, okay, so you see MgO, and I want to compare with LiF. Okay, so MgO, okay, is going to be, we are dealing with Mg2 plus and O2 minus, Li plus, F minus. Okay, the thing that will affect the lattice energy is going to be the ionic size and also the ionic charge. And you can see here that the main thing that we can see over here is the charge. Okay, you can see MgO has more charge. So that will indicate that they are going to have more charge density. If they have more charge density, it means the bond between Mg2 plus and O2 minus is going to be greater. So that will release a lot of energy, more bond making. Yeah, bond formation is negative. So you are going to get more exothermic or more negative value of your lattice energy. So you can say the magnesium oxide, okay, is going to be more negative compared to lithium fluoride. Okay, this is how you compare. And let's say we are going to compare the second one. Okay, compare the lattice energy of lithium fluoride and potassium bromide. Now, lithium fluoride and potassium bromide, if I write it down, LiF, KBr, Li plus, F minus, K plus, Br minus. Okay, they have the same charge. So what we need to look, we have to look at another factor, which is going to be your ionic size. Okay, let's look at the size. Okay, lithium. Okay, if you have lithium in your periodic table, lithium followed by potassium. If you have F and then followed by Br, okay, it's not. If you look at the FClBri, okay, you can see the Br is lower. Okay, so generally, okay, if you look at K and Br, you can say that the size is bigger. Okay, compared to Li plus and F minus. So if they are bigger, okay, and they are having the same number of charge, okay, the charge density between LiF is going to be more, okay, because it's going to be smaller, okay. So if they are more, there will be more forces of attraction, electrostatic forces of attraction. So they are going to give you a more exothermic value, or which is going to be more negative value. So you can say that, okay, if I just select LiF, okay, this is going to be more negative. Okay, the lattice energy is going to be more negative compared to potassium bromide. So please remember this. Okay, how do we use the factor, okay, for affecting the lattice energy, and we are going to use them to compare. Very, very important. Yeah, very, very important. Okay, so let's actually move on. Okay, this is part of the atomization. Okay, atomization is part of your AS topic. Okay, so it is important also to know about this because we need to use it for our born-haber cycle later. Okay, so if you look at the definition of enthalpy change of atomization, it's an enthalpy change when 1 mole of gaseous atom is formed from its element under standard condition. okay, lithium, okay, the element under standard condition is going to be solid, okay, it's a metal. And then you are forming 1 mole of gaseous atom. Okay, so 1 mole of gaseous atom is being formed. That is going to be enthalpy change of atomization. Now, if I want to write down the enthalpy change of atomization, for example, let's say I want to write down for sodium, for example. Sodium is going to be solid, okay, and then you want to change it into atoms. So 1 mole of atom gases, okay, so this is going to be the equation for enthalpy change of atomization. Now, if let's say if I have Cl2, for example, Cl2 exists as gas as the under standard condition. So how do I write? Okay, am I going to write 2Cl? The answer is no, okay, because it's supposed to be 1 mole of gaseous atom. Okay, so you write down Cl gas. So how do you make Cl2 to become 1? So you just need to put half in front over there. Okay, and this is going to be the enthalpy change of atomization for chlorine. Okay, what happens if I'm dealing with Br2? What happens if I'm dealing with I2? It is very important that you know the standard condition, under standard condition, what is going to be the state. Okay, because we have learned group 17, you should know that Br2 is going to be liquid under standard condition. I2 is going to be a black solid. Okay, if you remember, okay, it's going to be solid. So you are going to get 1 mole of Br, 1 mole of I, which is supposed to be in gas. Okay, so what we need to do, just put half over there, just put half over there. These are all going to be the equation for enthalpy change of atomization. So if you look over here, okay, when I mentioned about lattice energy, I mentioned that very important, remember, is always exothermic. Okay, so for when you look at the enthalpy change of atomization, what is going to be very important over here? The very important part over here is going to be, since atomization is going to be from solid changing into gas. Okay, because solid normally, okay, when you look at sodium itself, sodium, they tend to become form a giant ionic lattice. So if you want sodium to become a single 1 mole of atom, okay, you are breaking the bonds between the lattice. So we are talking about atomization is more towards breaking of bond. So if you're breaking bond, okay, do remember it's going to be always going to be endothermic. It's always going to require heat to break the bond. So this is going to be endothermic, always. Okay, always remember this. Atomization is always endothermic. Now, let's move on. Okay, write the equation for the atomization. So we write, okay, I think I already written this. Okay, you can refer over here. So I'll just bring it over here. Okay. If I copy, okay, I'll just put it over here. Okay, so this is going to be the answers for this. Okay, you can see. Okay, write the equations for atomization of chlorine, bromine, and iodine. Okay, now, if you look at the second question over here, the bond energy of chlorine molecule is 244. Okay, where do we get this bond energy? You can refer it from your data booklet. Okay, data booklet. What is the value of enthalpy of atomization of chlorine, for example? So if it is bond energy, okay, it means the energy required to break the bond between Cl and Cl. So when you break the bond, you are going to get 2Cl. This one you need to understand, yeah? So the bond energy, it means that you require 244 kilojoules to break, okay, to break the bond, and you are going to get 2Cl. So if the question is, what is the value of atomization of chlorine? The answer is not going to be 244. Please remember this, because atomization, if you look at the definition, is 1 mole. You can see 2 moles is being formed. So if you want 1 mole, okay, your bond energy must be divided by 2. So always remember the value of atomization of chlorine is half of the value of your bond energy. So instead of 244, it's supposed to be 122 kilojoule per mole. Okay, that is going to be atomization. So if I have an equation over here, for example, they put 3 over 2 Cl2, okay, to give you 3 moles of Cl atom of gas over there. And then they are telling you, okay, what is going to be A, for example. Okay, so if you are looking over here, okay, if you are having atomization, which is going to be 122, you should know that this is because 3 moles of atom is being formed, you need to times by 3. So what you need to do is 122 times by 3. You will get 366. okay, that is going to be the value of A. Now, can I find the value of A by using the bond energy alone? The answer is definitely yes, okay, but it's not going to be similar by times by 3. Please remember this. You are going to break the bond of 3/2 moles of Cl2, okay? So if you are breaking 1 mole, you are using 244. So if you are breaking 3/2 moles of Cl2, okay, what you need to do, you need to break, okay, you need to break 3/2. Okay, so I think I'll try to share again. Yeah, I think something wrong over there. Hold on. Okay, but if you can still see what is on the screen, okay, you can see. Okay, hold on. Yeah, just give me a moment. Okay, you can see that, okay, if I'm using bond energy alone, okay, what I need to do is I need to put 3/2 times, okay, the bond energy of the Cl2, which is 244. Okay, when you do that, okay, you are going to get 366. Okay, so please remember, okay, there is going to be additional stuff that you need to do, yeah, if you have the bond energy. When do I use this? Because most of the questions in your past year paper, okay, if they are talking about Cl2, O2, and so on, they will not give you the enthalpy of atomization. Okay, if you find any of these values are missing, the only way to look for them is by looking at the bond energy. You can still solve them. Yeah, you can still solve them. Okay, so I'll just move on. Okay, later we try some questions related to that. Okay, I will move on to this first ionization energy. Now, first ionization energy is also a content from AS, okay, where it's going to be the energy required to remove 1 electron from each atom in 1 mole of atom of the element in gaseous state. So I think if it is too much, you can just refer to the equation over there. If I have calcium must be in gaseous form, then only I remove the electron. Okay, so if I'm going to have the first ionization energy for sodium, so I need to change the sodium solid. I must change it into gas first, then only I remove the electron to become Na plus gas plus electron. So this is very important. And what is another thing that we need to take note over here is going to be, you must remember, since you are removing the electron, okay, so you are having an atom, you're removing the electron, you are breaking the bond. Okay, you're breaking the bond. So therefore, okay, anything that is involving breaking the bond is always endothermic. So I put it over here. It's always endothermic. Okay, so first ionization energy, second ionization energy, and third, okay, they are always endothermic. Okay, but I think when you learn in your AS, you should know the successive ionization energy will increase. Why? Because as you keep on removing the electron, they are going to become more positively charged. So they are going to hold all the electrons closer to them. So it's going to be difficult to remove the second, third, and so on. So the successive ionization energies are going to be greater. Okay, but that one I leave it to you. You revise for your AS. Okay. Now, if you look at the checkpoint over here, okay, so if they ask you, okay, to write down the equation for first ionization energy for sodium, for example, okay, so sodium must be in gaseous form, and it is going to become Na plus gas plus electron. Okay, this is the equation. So if you want to write the second ionization energy for the magnesium, so you have removed 1 electron from magnesium and you need to remove 1 more. So they are going to start from Mg plus, then you are going to have Mg2 plus and then plus another electron. But please remember, they must have gas. Okay, very important. And then describing the trend of first ionization energy across the period and down the group of the periodic table. I think this one everyone should know. So if I just put a periodic table, let's say, for example, I just roughly put a periodic table over here. So what normally we need to remember, the first thing, when you go across any period, okay, you will notice this particular trend. Okay, the atomic size, generally they are going to become smaller and smaller. Okay, you should know, okay, why it is getting smaller and smaller. Okay, because the same number of shell, okay, But what happened is the proton number is increasing. When the proton number is increasing, they are going to hold all the shell and all the electrons closer to itself. So they become smaller. So now your work now is you want to find out, I want to remove one electron from it. So I want to remove the electron from here, and I compare with the electron that I remove over here towards my right-hand side of my periodic table. You will notice that the one that is on the right-hand side of the periodic table, because they are smaller, okay, there is going to be a huge attraction of the nucleus towards the electron. It's going to be harder to be removed. So when you have difficulty to remove the electron, it means your ionization energy is going to be greater. That's the reason why when you go across the periodic table, okay, the ionization energy increases. Okay, this one will apply to first, second, third, and so on. Okay, generally they are going to be the ionization energy will increase across the periodic table. Now, what will happen? Okay, if you go down a particular group, okay, one of the things that you need to remember is the size generally increase. Why it increase? Okay, because increase in number of shells. Okay, because different period number of shells are going to be different. And you also need to know, okay, the proton number also increase. Okay, I'm not going to deny that. But always remember, okay, there are three factors that are influencing over here, which is increase in your proton. Okay, we also have increase in your distance because of the shell. Okay, distance of what? Distance from the nucleus and the electron. And we also notice there is going to be increase in number of shells. Now, what will happen because of the increase in number of shell? We have what we call a shielding effect. Okay, shielding effect is going to be it's a force, okay, that will prevent the attraction or weaken the attraction of the nucleus towards the electron. So what you can say over here, even though there is an increase in proton going down the group, your increase in distance and shielding effect will outweigh, okay, will outweigh. What is outweigh? They are going to be given more importance, okay, compared to increase in proton. Okay, they will outweigh the increase of proton. So it means that the nucleus will not have enough attraction, okay, towards the electron. So what does it mean? If I want to remove the electron over here, okay, don't have attraction, the nucleus don't have a proper attraction towards the electron, I'm going to remove this easily. So if I'm able to remove the electron easily, going down the group, I can conclude that, okay, my ionization energy decreasing. Okay, my ionization energy decreasing. All your AS content. Yeah. So if you look at the definition and so on, okay, if you look at the describing the trend, I have done it. Yeah. Now, what is included in your A2? Okay, this one, okay, very important because we are using a new syllabus now. If you are still using the old textbook, okay, this part will not be discussed properly in your old textbook. Okay, please use the new textbook and also refer to the syllabus. Okay, they have included new things, okay, related to electron affinity, related to trend. Okay, so I will discuss about that as well. So the definition, let's start with definition. So electron affinity is enthalpy change when 1 mole of electron is added. Just now, ionization energy you remove, but now you are adding the electron. So how do I write it down? Okay, like for example, Cl. Okay, again, it must be in gases. So gas, when I add 1 mole of electron, I am going to get Cl gas minus. So this is going to be the equation. So this is going to be the first electron affinity. Okay, so second electron affinity, if there is, like for example, let's try maybe oxygen. Oxygen, first electron affinity will look like this. And they are going to give you O minus gas. But we know that, okay, O minus, okay, the gas can add another electron to give you O2 minus gas. So this is the first electron affinity. I'll just use EA, electron affinity. And then the second electron affinity. So you can see that. Okay, so they are going to be similar to your ionization energy. Now, what we need to know over here is going to be the trend. Okay, later we can talk about the trend. But okay, what is important, very important over here is you are adding electron. Okay, you are adding electron. When we are adding electron, we are forming bonds. Okay, we are forming bonds. And I told you forming bonds, okay, it must be releasing energy. Okay, releasing energy. So it's exothermic. Okay, it's exothermic. But do remember, it is only exothermic when it comes to your first electron affinity. First electron affinity only. Okay, but okay, your second, third, and so on, okay, the others, okay, will be different. Okay, I will show you in a simple way over here. If let's say a person, a neutral person, okay, you are removing, you are adding electron. Okay, you added electron. Let's say this is Cl. You added electron. Okay, so they will become Cl minus. Okay, Cl minus. Okay, that's my first electron affinity. Now I have Cl minus, and I'm trying to bring in another electron, which is a negative ion. Okay, which is a negatively charged. Sorry, negative charge. You can see that this is negative and this is negative. And you should know negative charges repel. Okay, when negative charges repel, what you need to do, you need to provide additional energy to overcome that repulsion. Okay, to overcome that repulsion. That's the reason, starting from the second and third and so on, it is going to become endothermic. Because why? There is energy required to overcome the repulsion between negative ions and the negative charge of the electron. Okay, so it will start with exothermic, but second and third, they will be endothermic. Please remember that. Okay, so here you see some of the questions taken from the textbook as well. Suggest why second and third electron affinities are always endothermic. Okay, the reason why they are always endothermic, because you need energy to overcome the repulsion, okay, between the equal charge of the negative charges of the ion and also the electron. Okay, and then writing equations representing first electron affinity of iodine. Okay, similar. Okay, iodine. Okay, you are adding electron. Okay, it must be in gaseous form. Okay, and you are going to get I minus in gaseous form. Second electron affinity of sulfur, you already added one electron. Now it's supposed to be S minus, must be in gas. You add another electron and it is going to become S2 minus in gaseous form. So you follow the definition. So what is important? First, ionization electron affinity is going to be exothermic, okay, because it is going to be forming bonds, okay, but second and third is going to be endothermic. Okay, let's move on. Now, this is very important. What is the trend? Describing the trend of first electron affinity across the period for the non-metals, not found in your textbook anymore, the blue textbook anymore. Okay, and then what is the trend of first affinity, electron affinity down groups 15, 16, and 17. Do remember, electron affinity, the trend, it is not a clear trend. Okay, that's why they are trying to put it very specific for your syllabus now. And they say that, okay, across non-metals only. What do you see? Okay, quite simple. You see, if you have a periodic table, okay, and we are looking at the non-metals, maybe around here only, okay, the non-metals. Okay, what I noticed just now, I told you the size, okay, they get smaller and smaller. Okay, so if the size is getting smaller, why it is getting smaller? Just assume, yeah, they have positive charge. Okay, why it is getting smaller? Because the positive over here is greater. Okay, it's quite great. Why? Because more proton, it will attract all the electron and so on. Okay, they are going to be smaller. Now, if I'm introducing a negative charge, which is going to be in form of electron, what will happen? They will bond easily. Why? Because more positive. Okay, they will bond easily. And when they bond easily, they're forming bond easily, they will be exothermic. So you can say that this is going to be more exothermic, or you can say, okay, this is going to be more negative, because we are talking about first electron affinity, okay, which is going to be a negative value. Okay, so here, okay, here is going to be more negative. Okay, it's exothermic, yeah, so please remember. So it's going to be a more negative value when you go across. So if I put it over here, what is the trend? The electron affinity, okay, the first electron affinity will become more negative. Now, what will happen if it is going to be first electron affinity down group 15, 16, and 17, the same? Let's say this is group 15, for example. And then the size is getting bigger and bigger. Why? I think I already mentioned to you. More number of shells, distance is more, okay? The shell and the distance will outweigh the increase in number of proton, okay? So now, if you compare the positive charge over here and the positive charge over here, the positive charge at the top is going to be much more greater. Okay, it's going to be much more greater. Why? Because it's small. Okay, it's going to hold everything closer. So now, if I have another electron, which is a negative charge, okay, and I try to bring them over here, the bonding will be greater over here at the top. Okay, so this at the top, you are going to get more exothermic or more negative compared to the electron that I bond over here, not so good bond. Okay, so if it is not so good bond, they're still forming bond, they will be still negative, okay, but less negative. So you can say that, okay, the trend from more negative to become less negative, I can say that the trend is it will become less negative down the group. Okay, this is going to be the explanation. And you need to know how to explain, okay, like what I explained over here. I hope you can understand what I'm trying to say over here. Okay, let's move on. So here the definition, okay, standard enthalpy change of formation. Okay, before we do our born-haber cycle, it is very important to know about enthalpy change of formation. Okay, it's going to be 1 mole of compound is formed from its element under standard condition. So if I have 1 mole of compound, let's say for example NaCl solid, you are forming it from its elements, okay, under standard condition. The element that you can get for sodium, okay, sodium is solid under normal situation. And then if you have Cl2, okay, they are going to be gas under normal situation. So you just need 1 mole, so you just need to put half over there. Okay, this is the equation for enthalpy change of formation. So if I have another example, let's say I'm talking about MgCl2, for example. If I want to form MgCl2, how do I get it? Okay, so Mg must be in solid, and then Cl2, okay, must be in gas. So if they join together, okay, they give you MgCl2. Now, what is important over here? Okay, don't get cheated with this term here, formation. Formation is always forming bond. No, it's not really. Okay, always remember, okay, whatever that is being formed and so on, it involves energy, bond breaking and bond formation. Yeah. So for formation, okay, please remember it is not always. Yeah. It can be both. Okay, it can be either endothermic. So I'll just put it over here. It can be endothermic. It can be also exothermic. So please remember this. Okay, very, very important. Okay, endothermic or exothermic. So it's not fixed. Okay. Now let's look at this checkpoint then. Okay, so here enthalpy change of formation of calcium oxide. Quite simple. Calcium oxide solid. You are going to get it from calcium solid. Oxygen is going to be gas. Okay, and then you want CaO, so I put half over there. Done. Okay, enthalpy change of formation of iron 3 chloride. So FeCl3 solid. So I am going to get it from Fe solid, and then Cl2, okay, which is in gas. So I need 3. So how do I get 3? 3 over 2. Okay, so you just write like that. So let's move on. Okay, calculate the lattice energy for sodium chloride. The entire thing that we have learned today, okay, is all comes down to this. Okay, how do we calculate lattice energy and why we need to calculate? Please remember, lattice energy cannot be determined directly from experiment. You need to do calculation. And what calculation? We have to use the Hess's law. Okay, you need to know the definition of the Hess's law as well. Okay, the total energy is independent of the route taken. Yeah, so that is AS. Okay, but now you need to know how to draw a born-haber cycle. Okay, so this is very important. So now always remember, when you want to draw this, always start with the formation. This is the first thing that I will tell my kids. Okay, start with the formation. To form what? NaCl. Okay, you put a line over there. You put NaCl, solid. Okay, and you are forming. Okay, so if it is forming, you see negative. Okay, you just put negative. How do you write equation for forming? You form from its element 1 mole, okay, of NaCl from its element must be from sodium solid and must be from half Cl2 gas. Okay, this is important. Okay, and this one I put negative 411 over here. Next, okay, atomization. So you see, you just put like this, and then you put Na gas. Okay, so this one half Cl2, just rewrite again. This is going to be atomization 1 mole, so it's going to be 107. I just put 107. You atomize the Cl. From Cl2 becomes Cl. So how? Half Cl2 will automatically become Cl. So no need to times by half and so on. They will become, okay, Na gas, okay, plus Cl gas. Don't think that gas, no need to change into gas, just leave it like that. No, you still change into atomization. So this is going to be atomization of the Cl, which is going to be 122. Next is going to be you ionize the sodium. Sodium, if you want to ionize, you must ionize from gas. So it is important you do atomization first. Yeah. So now I'm going to ionize the sodium. So first ionization energy. So I have the electron, okay, and then I have the Cl still stay. Okay, so this is going to be my first ionization energy, which is going to be 496. And then the next is going to be you want to have the electron affinity, the first electron affinity. So you join them, okay, and do remember the first electron affinity is negative. Okay, so what you need to do, it will become lower. Okay, so you put like this, and then they will come lower. And this is going to be Na plus gas, and then you have Cl minus gas. And this one, okay, is going to be written for, here is going to be negative 348. And the last one, okay, is going to be lattice energy. What is lattice energy? You form 1 mole of NaCl solid, okay, the ionic compound, from its gaseous ion. So this is lattice energy. So you calculate. How to calculate, I think you should know, yeah? So this one depends on your teacher, how they taught you, okay? Normally, you can use the Hess's law, okay? So normally, I teach my students clockwise equals to anti-clockwise. So what I do is I just change this, okay? Put a circle there. Just put like it follows the circumference over here. This is clockwise, clockwise. This is coming down, also clockwise, okay? And then this is also coming down, also clockwise. This is going to be going like this, okay? It's anti-clockwise. So when I write down the equation, okay, it will look like I am going to write down like 107 plus 122 plus 496 plus negative 348 plus lattice energy equals to negative 411. If you calculate, and you will get this lattice energy. Okay, this is very important. Okay, you can just calculate. Now, the born-haber cycle for magnesium chloride. Okay, the born-haber cycle for aluminium oxide. Okay, I will give you the notes for this, how to draw and so on. Okay, you can try on your own. Okay, so similar way. Okay, similar way. I think we can focus more on how to write the born-haber cycle for the aluminium oxide more. Okay, because it involves 3 ionization energy. First ionization energy, second, third, okay, until it becomes Al3 plus, and also involves some numbers that you need to times, like Al2O3. Okay, I have prepared. Okay, I have prepared for you. Okay, I'll show you what I prepared for you. It is already shared for you, so you can just go through that. Yeah, so you can just go through. Yeah, aluminium oxide and also for magnesium chloride. I will share this later. Yeah, it's already shared in the Google site. You can have a look as well. Okay, but now, okay, if I just continue, okay, if you look at this, some questions, okay, that we can get it from past paper and so on. Okay, maybe I'll just go through one of the example here. Okay, and then you can also go through this second one on your own. Okay, But what I want to show is going to be sometimes, okay, you have a situation where you need to use the bond energy. Okay, this is some of the situation where you need to use the bond energy. So you see, write an equation to represent the lattice energy of PbCl2. Okay, show state symbols. Okay, so PbCl2, okay, is going to be solid, and you are going to get it from Pb2 plus gas, and then Cl minus must be gas, and then put 2 there. So this is going to be the lattice energy. Okay, this is the symbols also, very important. Now use the following data together with appropriate data from the data booklet. Calculate a value for lattice energy for PbCl2. Now, this one I told you, okay, if you want to calculate, always start with formation. Okay, so I'll just start like with formation. I just put over here, I have PbCl2, solid, and it's going to be negative. I just put negative. How do you get PbCl2? I get it from Pb solid, okay, formation, yeah. So it comes from Cl2 gas. Okay, so I have this. Okay, this is going to be my enthalpy of formation, which is going to be negative 359. And then, okay, the next things that I need to do is going to be, I need to do the atomization. Okay, so first, okay, I do the atomization of Pb. So Pb become gas. Okay, so this one stay. So when the Pb change into gas, it's going to be 195. I just put 195 over there. Now, the next step is going to change the Cl into atom. Okay, Pb gas is already there. Cl will get a change into 2Cl. Okay, so there is no data for atomization of Cl. So what you need to do, you need to go to your data booklet. Okay, look for the Cl and Cl, homonuclear bond energy. So what is bond energy? Okay, you are breaking the Cl2 to become 2Cl. So that you require 2 for 2. So here, you do not need to actually say, oh, this is 2 moles of Cl. I need to times 2 for 2 times 2. No, not really. Follow here. Cl2 is going to change into 2Cl. Okay, so what you need to do, you need to use the actual 2 for 2. Okay, 2 for 2 because Cl2 changing into 2Cl. So this one must be 2 for 2. Okay, that is done. Then after that, you look into the first ionization energy and second ionization energy. So you need to draw, okay? Like for example, put Pb plus 2Cl. Then you put another Pb2 plus, okay, plus 2Cl with the electron, and then 2 electron, and so on. Okay, once you get that, okay, let me make it smaller. Once you get that, okay, you need to also look into the electron affinity of chlorine. Okay, so do remember the electron affinity of chlorine is negative. Okay, so the electron affinity will go down. Okay, when it goes down, okay, do remember you have 2Cl plus 2 electron. It means 2 atoms of Cl adding 2 moles of electron. So you are talking about 2 times electron affinity, not twice, 2 times electron affinity, which is going to be negative 349. You are going to get Pb2 plus gas, and you will get 2Cl minus gas. And the last thing is just bring over here, you will have your lattice energy. Okay, and use the same method how to calculate for the Hess's law. Okay, clockwise equals to anti-clockwise. Okay, here is going to be this one plus 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 lattice energy equals to negative 359, and you will get the answer. Okay, the answer, if you want to check, is always there. Yeah, you can check. Now, how might the lattice energy of PbCl2 compare with PbBr2? This one is the factor affecting the lattice energy. So how, okay, you're talking about Pb2 plus, okay, you're talking about Pb2 plus, nothing to do with the charge now, okay, we are talking about Cl and Br. Always remember F, Cl, Br, I, okay, the size is getting bigger and bigger, okay, so Br is bigger, okay, compared to Cl, okay, so if it is smaller, okay, Cl being smaller, they are going to have more charge density. Okay, so if they are going to have more charge density, they are going to form better bonds, okay, with Pb2 plus. Okay, so they are going to be PbCl2, okay, is going to be more exothermic or more negative, or you can say the lattice energy of PbCl2 is going to be more negative compared to PbBr2. Okay, that is going to be, you can refer to there as well. Why and so on, you can refer. Okay. Okay, I think I got disconnected for a while. But if you continue, okay, if we continue the thing, okay, this one please try on your own. Okay, this one is very important. I think it's related on how you apply the equation. Okay, but try and see whether you get the negative 552. Okay, now that's it from me. Okay, but okay, there are a few things that I want you guys to do. Okay, the first thing, okay, this one now is 223. Okay, we are going to try quizzes. Okay, I will start a live quiz now. Okay, so we are going to, all of us, okay, we'll try the quiz for today. Okay, hold on. Simple questions. Okay. It would be better if you can name yourself, okay, maybe from campus and then your nickname should be okay. So we will wait for a while and then we'll start. Okay, once it reach 100, we will start, okay, because of lack of time. Okay, but if you want to redo the quizzes again, I will put you another link, okay, and you can try, yeah. So it's just to test, okay, how far you understand, yeah, and so on. Okay, you can still join, okay, well, even though if I start the quiz now, okay, I will start the quiz now. Okay, just nice. We have another 2 more minutes to go. Okay, for some of you who have completed and so on, okay, I think we have a lot of people. Okay, you can continue. Okay, you can continue doing. Okay, there is another thing that I want to share to you as well. Okay, you can have a look in your chat. Okay, I will share the inside the chat. It's going to be, I will share to you a link. Okay, it's called a Padlet link. Okay, what I want you guys to do is to write the reflection for today. Okay, I'll show you how it will look like. Okay, so if you use the Padlet, okay, you will come to this here. Okay, so you just write a reflection on what you have learned for today's lesson. Okay, and also indicate the part, okay, that you are having trouble to understand as well. Yeah, so please write down. Okay, be responsible. Okay, be responsible of your comments and so on. Okay, because everyone will be reading this. Okay, write your campus and your name as well. So anyway, if you look at the, I think your teachers would have shared to you the BBS Speak Chemistry link. Okay, if you go to the website, okay, you can actually see under the announcement, okay, whatever that we learned today. Okay, you see updated with the lecture notes 1 and lecture 1 marking key. So you can check over there. The marking key is also there. Yeah, and then if you miss my Padlet link, it's there. Okay, and then if you want to try the quizzes again, I will put the link over there. Okay, you can also try the quizzes again. So if you just click over there, okay, it will link you to this chapter. Okay, chemical energetics. Okay, and currently we are doing the Padlet. Okay, the Padlet will appear here. Okay. Later we can see all together. Okay, and then also the notes for today, and then if you click at the answers for today as well, okay, it's also there. You can download. Okay, and you can actually use it for your own studies. Yeah, so that's it for today. Okay, I think if I look at your quizzes, okay, I think most of you, okay, 71 accuracy, I think some of you, okay, still doing. Okay, so if let's say, okay, you are not having good marks over here, okay, if you cannot get 50% and so on, okay, please remember you can try the quizzes again. Okay, I will open the link later. How to get the link? Okay, you just visit to my website. Okay, and the link will be there. Okay, you can just try the quizzes again. Yeah, that's it for today. Okay, I'll stop sharing. Okay, thank you very much, guys. Okay, you need to go to other classes. I hope you learned something over here. Okay, looking forward for the next lesson as well. Thank you, the teachers who are here as well. Okay, see you guys. Okay, take care.
Thank you, Mr. Bye, Mr.
Yeah, see you.